Good day. How are you today? We are going to look at analog inputs, and from what I've gathered, this is something that students have a little hard time understanding at points in their life. Once you get it, you get it. I think conceptually we understand how they work. So like in an average manufacturing environment, say this is a tank and I have a level sensor. It sends some type of signal back to the controller, and oftentimes, and the controller reads it, and then it sends some type of analog output signal to a valve to open and close. We get how this works. You know, I always use the example of a dimmer switch with a dimmer light switch. Like if I rotate it one way, the light goes dimmer, and if I rotate it up, the light goes up. That's like how an analog input works conceptually. But how do we program it in Allen Bradley or another PLC manufacturer? Well, again, this is a simple circuit here that we have, and usually what happens is this sends a signal of electricity of some type. Either it's going to be 0 to 10 volts, typically DC, or a 4 to 20 milliamp signal. Most of the time, those are the one or two ways that analog inputs or outputs, for that matter, send signals to the PLC, and then the PLC will process that voltage value and give it some type of internal value. But it's important that we understand this first, because if we don't understand the electricity side of things, we're not going to really understand what we're doing in the PLC program. So in this case, think of this process as we go through things, and we're just going to deal with the level sensor for today. That this is going to kind of fill up in some way, and it's going to then send a varying electrical voltage signal to the PLC. But then the question is, okay, that's simple enough, but how does it really work? Because in our heads, and this is what's hard for a lot of students to get, is actually they think that the PLC input card is going to generate the electricity that will then adjust that up and down. But in reality, what we are doing is treating this kind of like a glorified digital multimeter. That all this is doing is, in theory, measuring. So this is a voltage source, and if you take a look right here, take a look. Here's a power supply powering it, and from right here to right here, you can see that this voltage channel 1 in is going through here, hooking up right here, and then measuring here. That would be like me having a digital multimeter just measuring two contacts, taking my two little multimeter probes and measuring it like that, or like that, if you want to keep your polarities right. Because that's all an analog card is really doing, is just measuring like a digital multimeter. And instead of employing someone to read this value and writing it down all the time, the PLC is reading it for you. But if you start thinking of analog inputs in that terms, then you will realize I need to typically have some type of power supply to power the sensor. Because if the power supply is powering the sensor, what this is basically acting as then is some type of variable resistor, and it's oversimplifying it, I know, that it will then adjust the voltage that you're reading at your digital multimeter. And for class, guess what we have? We have a potentiometer that we are going to use to vary the resistance inside to thus change the voltage. Revolutionary, I know. Now, currents operate differently, because remember, how do we measure current in a line? We measure it in series. So in this case, I still would need some type of power supply and then I just put in a current transmitter, or basically of some type of variable resistor that will then throttle the current that I read on my current input. And then what you'll notice in this case is that in my channel 0, that will then ground out to my common here. So again, you're only, think of a digital multimeter as you would hook it up, just like how you would hook up a digital multimeter out in the field. So if I want to work with a 4 to 20 milliamp sensor, I need to get my card set up in a way so it's measuring a current like I would with a digital multimeter in the field. Or voltage. Set things up so that I'm measuring it in a way that's across the component to measure the voltage drop, like I would with a digital multimeter. So if you start thinking along that lines, the mystery kind of gets solved. But let's talk about our trainer and what that looks like. This is our trainer. We're going to work with a pot, or that's what that is. That is a rheostat, a pot, a potentiometer. That's a technical term, but I'll just call it a pot. And you'll notice that there's a resistor in front of it. I want to highlight that sometimes when you're working with analog signals, most control circuits are 24, but what did I just say that this operates off of? Probably 0 to 10 volts. So you're going to have to do some type of signal conditioning. Either, a lot of times, this is the cheater way, put a resistor in series with it, and then that will make the voltage drop something to 10 volts after that, and then you can use this like a pot or some type of sensor to adjust that sensor. Sometimes you'll see a second power supply, so you can actually put that into a power supply, and then it will drop it down for you. I've seen that as well. In some instances, you might need to do that, but be aware that I can't just go off my line straight into my potentiometer and then the signal wire into the VN. I can't do that. Okay. And if you take a look, here's my resistor, here's my hot in, and then I'm basically measuring the signal wire, and then the out is being linked up on the back side of my negative. So it's reading to like a potential ground, for instance. And then down here, all of it's going into the analog common. So ANLGCOM. I wanted to highlight this more. And then the common is going off until the 24 negative, or or 0 volt, or the negative. Okay, so that's how the wiring for our analog cards are looking like. Just for the input side. I didn't do the output side because that's going to be next week or another time. But this is how the schematic looks: 24 volts, resistor in series, and then yada yada yada. So keep this in mind. So what this is doing is setting the voltage different, and is basically reading a voltage difference, isn't it? Yeah. And that's what we're going to do in class. Is we're going to literally set up a multimeter from here to here and read that voltage drop and then compare, just to get you a handle on stuff. But then the question is, what does the processor do with this information? What does the processor do with this information? And what it does is normalize is the proper term, but I'll show you what that means in a second, is change that value into some type of digital readout. Because how does the processor remember stuff? In a combination of zeros and ones. We use data, like we use the verbiage, store it as an integer, which is a 16-bit string of zeros and ones that will represent something. And if you do the math, 16 bits should get you close to that as your as a value. So if you do 16-bit binary, or in this case 15-bit, because they need to add a sign in there, it should get you close to that. I don't feel like going through that math. But that is the maximum digital value. And how this is set up is that if the input card is reading 10.5 volts, it should register this digital value in the processor. And when we program, and I'll show you an example of this, all we're going to see is numbers that look like this. We're never going to see something that looks like this. Because in reality, what we have, going back to our tank analogy, our tank, is what we care about is not what the voltage, so this is the tank, we don't care about the voltage that or the raw value that this is reading. What we're trying to understand is how high is this in the tank? So is it 25 feet, 25 feet, 3 meters? I don't know. But setting everything up this way allows me to, in a very real sense, what this will do is we're going to take a real world value of feet, for instance, use a sensor to translate that into a voltage. That will be translated into a digital value. And then in my program, and I will change that digital value back into the real world value. And this is the trip up, because this requires math. Because if I just talk about electricity, we get this. We can kind of understand about the digital value. What trips people up is this real world value going to real world value. And we do it this way because then I can change the real world value from feet to maybe temperature, maybe, or flow, or something else, and not have to change how we process it at all. But if I had to process everything differently every single time, if it's temperature or height or I don't know, capacity or some other made up term that we, volume, I don't know, whatever you're trying to measure, then this gets more complicated. But if I just stick to the voltage, so how this affects voltage, how then this voltage or current affects the digitized value in the processor, then I can say what to do with this digitized value that will then get me to the real world value. So to show you this, what we are going to do in class is, as I said, we're going to take a potentiometer and move it to various different levels, like 0, 1, 2, 3, 4, 5, 6. While we do that, we are going to measure across that voltage, and we are going to get a voltage. We're going to record that. And as we're recording that, we're going to then go to the processor. And this is how things work in the processor. If you notice, I have an analog card right here sitting there that's been added. That should already be there. And a lot of this information I got from the tech documents of that analog card. Because if you learn to read tech documents, that's all the textbooks you need a lot of times. But if I click on this, it's going to open up, and different input cards have more bells and whistles, and I'll open up one in a second. But here it's going to give me input connection. Before you can actually get it to register, you would need to enable the channel that you want. Because these can be kind of power hungry and other things, we may not enable everything, and because the more you enable, the more interference you could have. So enable channel 1 for our trainer. Hit OK. And now, if I go online, I can look at my controller tags and see what happens when I change things. I'm gonna hide that for a second so I don't confuse you. But if I go into my controller tags, you'll see, since this card is on my bus connected, it's local, but it's in slot 2 and it's an input, you'll notice right away that things look slightly different. So local to slot 2 input, but because this is analog, it's a number, it's not a 1 or 0, so it's going to record an integer. But we've enabled channel 1, and now since it's off, watch what I do when watch what happens here when I start to move things. Though I am changing voltage with my potentiometer, it is reading as some digitized value. Something, so it's reading something that looks like this, doesn't it? So 7, and if I keep turning it up, I'll crank it all the way up, and I get up to my upper end, which is close to that 3101. It's not 100% right, but we might need to eventually calibrate and other things, but that's another story for another day. Now, some other input cards may allow you some other things that you can, some other information. So I've added another input card that's on our distributed I/O, but we have no inputs tied into that. In class, we could do that, but I don't have a lot of potentiometers and other things that we could mess with. But notice some input cards will give you the ability to set up a high-level, low-level alarm, whether to calibrate. But now, right now, it's giving a fault because nothing is plugged in. And if I open the card here, which this is another input card, you can see I can do some configuration, and I can adjust its voltage range if I want to. I can give a small filter, and I can do the high and the like a high and a low. I can also configure alarms based upon the voltage. So this might not even necessarily kick out the digital value because it's already calibrating it for me, potentially. So you always need to check with the technical documents to see how it's kicking the value out. I haven't played around with this card, so I don't want to speak much more because I don't have any inputs, but I wanted to point out that some of the Control-Logix, some of the higher level end cards would give you the ability to turn on low level alarms, high level alarms, and allow you to adjust things. So I can, move it up, move it down, etc. by my cancel. And you can see some of that in there. So your fault, the status is there, and then it gives you your channel data. And if you look at the channel data, it's saying it's overrun, or something. So you can say high alarm, high alarm, because it's kicking it back, not as a digitized value, but actual voltage. So be aware. But what I'm doing is kind of giving you this is doing this for you. I'm doing the simpler, or not the simpler one, but just show you the process a little bit more. So in class, we're measuring the voltage, and then we're going to our local 2 channel 1, and then we're going to read this digital value right here at the different various places, because eventually the plan is for us then to graph out the voltages, and it should look something like this. So when I read, when I read the digital value here of like 3600, it should give me a rough voltage of 1. So we're going to read the voltages, and instead and you can see 3, 4, so it's kind of setting things up for you. I'm sorry, my drawing is bad, and you can see. But for me, in my process, I need to normalize it with the digital value on my X and my voltage on my Y. Because in my system, I'm going to take this digital value and then change it into something else. Now, in our system, we're going to say voltage just to compare what our multimeter, but instead of voltage, I could say temperature. And I could say that instead of this being 0, it could be 137. I don't know. Because what we're going to do in our system is be able to use some type of linear math that looks like this. Excel has this nice feature called add a trend line, and it draws a line that best fits this. And a little bit of review, this is a slope, this is a y-intercept. When I'm working with analogs, it's important to kind of know this, because if I want, so this is the how, if I multiply a digital value by this number, now I don't need to add this because we know 0, 0, this is just kind of guesstimating, but say if I multiply this number by my digital value, it should give me the voltage. So saying that one of those digital values is equal to so much of the like a point what 300 microvolts. Just go with it. This is the y-intercept. This is how much we shift this up here. So for instance, if I really, so if I'm doing temperature Fahrenheit, when does water freeze? 32, correct? If I wanted this to be actual temperature, I would make this 32, and I would do some type of math where I would get in, say, the digital value that I'm looking for is equal to, you know, and what I maybe, and the easiest thing is, you know, when it's 32, yeah, and then 30, you know, the easiest thing to figure out this is to take, you know, your temp high minus your temp low divided by your digital value high minus your digital value low. So if here, if the digital value was 0, you know, you would put 0 here, and what your digital value high is going to be like 3100, because that's the most I can do. This is pretty much always going to be the same. But if this is your temperature high, here would be 112 minus 32. I think it's going to be 1.8 from my memories. You should get this to be 0.0058 x plus 32. If you want to use this potentiometer to mimic something measuring temperature from 0 to boiling of water. If I didn't mention it, 212 is a boiling point of water in Fahrenheit. Just go with it. But that's my temperature range I wanted to monitor. This will always be roughly the same, but this is how you would put this into that to normalize your analog value. Okay? And this would just be how much you're basically where you started at 0. So you can shift it up, shift it down, whatever have you. Okay? And I just did the boiling point of water. And in this case, I would make this and that equal. Pretty fun. I know you love math, but a lot of times in Allen Bradley world, they'll make it easy for you a little bit. And so they showed you how to, in this case, find volt and do input scaling, and give you an example. So in case you forget, it's there. I'm going to point it out. But notice they kind of do the same thing. Your input data value, that's your digitized value, times your volts divided by significant bits. Well, I can kind of factor this in, and honestly, little secret, if you take this value here and divided it by this value here, you get 0.3. You get like what we had on the other sheet. You get this value right there. So you can still do this in the field, with the method I just showed you. This just, they know this. They know this value because they set it up. So you could, all right. So how can I do this in programming land? Well, there is a command. There's a command, and let me pull up my main routine, called CPT, or compute. And basically, instead of doing add, divide, multiply, and what we've been taught in math is if I do add, subtract, I can do all of this in a complex system, but sometimes that gets tedious. We can use the compute feature. And let me delete this and show you how to set this up. Again, I would always use a real number in this because I'm using division or something else. So with math, it gets a little hairy. So I always use a real data value. And so under compute and math, there's that CPT. And now first, the destination is where I want, basically what it equals, where I want to put a value into. And so I put a real data value, but expression is where things get a little bit more complicated. I can put my tags in directly. So I can browse my tags by clicking the little price tag, and I can find my local 2 input channel data 1. It should show up there, and then just like I would in Excel or a graphing calculator, times, and I'll just do my equation I just did, 0.0333 here. So I'll put this 0.003, and I'll just leave it at that, okay? But if I wanted to, I could hit plus. It does follow order of operations, but I always like putting in parentheses because I don't trust things sometimes. Plus 0.0, whatever have you. So what we just had there. So, okay. And if I hit OK, no errors, everything's hunky-dory. But see how I just match that almost verbatim there. Download. And now look, as I increase, I'm halfway right now. Look, it's right about 5 volts. Not exact, but there could be some. Now I cranked it up all the way up, and look, it's fairly close. Now, yours is probably gonna be closer. I'm just showing you for demonstration purposes. I kind of just put some random values in to match my voltage. But it's fairly close. And the more accurate, more points you have, you can normalize it more. But let me do the temperature analogy. I'm gonna go in here and change this to say, so it was 0.58, and I'm gonna add 32. Okay, accept changes. And now, oh, I think I was off by it. Oh, got one too many decimals in there. Whoops. I only need 2 zeros. Ah, that's better. And now, hey, look, that looks more like it. And the lowest value is 32. So if I was using this to monitor temperature, you can see how I just adjusted things. There's an easier way of doing this in function block, but I'm not going to go into that right now because we're not talking about function block programming. In older 500 models, there used to be a command called scale. Well, that got moved to function block, so you can only do it if you have function block enabled. So this is the other way of doing it, and that's just so I can teach you the theory. hope this clarifies stuff a little bit more. I know this is a little longer, but again, I hope you learned a little bit about analog inputs. And now I could take this value, move it to an HMI on my display panel, or you do other things with it if I need to. Okay?